So hello and welcome again. In this video we will look at a very important chemical called ammonia in terms of its production via a reaction called the Haber process, its uses, and how we can test for its presence. Well, the first very important thing to establish though is what is ammonia? Well, ammonia is a compound with the formula NH3, as can be seen in the diagrams here. That is, nitrogen bonded to three hydrogens in a covalent structure, as both nitrogen and hydrogen are non-metals. Nitrogen has 5 valence electrons, so you can see as well as having its 3 bonds, it also has that lone pair. It is a moderate base with a pH of around 11, and for some context, this is stronger than, say, baking soda, but far less basic than most hydroxides, such as sodium hydroxide. It is important to note that ammonia is a very important compound due to its uses in the food industry, and we'll be looking more at its uses in the food industry in a later video. Naturally, a compound that important needs manufacturing on a mass scale, and for this we use the Haber process. And there it is. This is an absolutely vital process in industry. The reaction here, as I briefly mentioned in the first video, is nitrogen and hydrogen making ammonia. As a small, quick exercise, can you work out how this will be balanced? Well, it's 1 nitrogen mole added to 3 hydrogen moles to create 2 moles of the product. Remember that little symbol for reversible reaction? There it is again. This process is done in industry using, well, a very complex piece of machinery. Here it is, and you can see here that nitrogen and hydrogen are both adding at the top, going into a compressor and then passing over some iron catalyst beds. After this, they go into a cooling tank and the ammonia goes out at the bottom, whereas any unused nitrogen and hydrogen get recycled, so nothing is wasted in the process. Now, as I mentioned, this is a reversible reaction, meaning that the nitrogen and hydrogen can be reproduced from the breakdown of ammonia. But obviously, we want this to not happen, because in industry, we want to make as much ammonia as we can, while making sure as little of that turns back into the elements it's made from. As such, we require a very specific set of conditions. And those conditions are 200 atmospheres of pressure and a temperature of 450 degrees Celsius, as well as the use of, as mentioned on the last slide, an iron catalyst. Now, this raises a number of questions. Firstly, the majority of reactions, including this one actually, just increase their rate as temperature increases. Why don't we just drive the temperature up far further to make much more ammonia in a shorter time? Well, in short, this is part of the nature of a reversible reaction. It's basically this point here, and this is going to sound confusing at first, but by putting the temperature far beyond what we are here, the reaction actually begins to go back far more the other way. You see, all reversible reactions are exothermic one way and endothermic the other, and in short, when the temperature is higher, the endothermic direction is preferred, because endothermic reactions absorb the heat from their surroundings, so doing this is more feasible here than giving off more heat to them. In this case, the endothermic direction is the ammonia breaking back down into nitrogen and hydrogen. So this raises the converse question: why not just put the temperature as low as possible? This is because the reversibility of the reaction, the equilibrium as you like, is independent of rate. Basically, when you're at higher temperatures, it's going faster both ways, though favouring the endothermic, and when at a lower temperature, it's going slower both ways, though favouring the exothermic. In other words, what we need is to find a point where we aren't producing ammonia too slowly to meet demand, but also not so much that the ammonia breaks down too much back into nitrogen and hydrogen. The pressure consideration is much simpler, and a higher pressure pushes the equilibrium towards the side with less moles of gas. Remembering that equation again, we can tell that the side with less moles of gas, that in the Haber process, is the side with the ammonia. Because everything is gas, so we have 4 moles on the left and 2 moles on the right. So the higher the pressure, basically, the better, and 200 atmospheres is a very high pressure. Note that the iron is there to increase reaction rate, but again, rate is independent of the equilibrium itself, and as such, will increase the rate without having effect on the equilibrium overall, because that is affected by the temperature and pressure as detailed above. You also need to know how to test for ammonia and ammonium ions. This isn't difficult. Firstly, the test for ammonia is done using litmus paper. Litmus paper is red, but ammonia turns damp red litmus paper blue. Effectively, the same test is used to detect ammonium ions, but they must first be converted to ammonia, which occurs when the ammonium is heated with sodium hydroxide, because ammonium ions in solution form an acid. That's all for this video, and I do apologise it ran on so long, but I hope you followed it alright. In the next video, we'll look at the properties of sulfuric acid.